Hello, in this video we're going to look at how we multiply complex numbers. If we have our complex numbers in Cartesian form, we know how to do this. So let's do an example. I have here the complex number 1 plus square root of 3i, and I want to multiply it by the complex number also in Cartesian form, square root of 3 plus i. We are doing a distributive property, and we are using the fact that I squared is equal to -1. So we will get square root of 3. The other ingredient for the real part is going to be square root of 3i multiplied by I, so minus square root of 3. And then we are going to have for the imaginary part, we need to multiply 1 times I. And we also need to multiply square root of 3i times square root of 3, so plus 3i. So this is equal to 4i. So we can do this. Could be a little bit slow, but we can do it. The disadvantage is that we don't really have a geometrical interpretation of what is this operation doing. And we do have such a nice geometrical interpretation if instead we look at how we multiply complex numbers when they are in polar form. So I want you to check that the polar form for the complex number 1 plus square root of 3i is actually 2 cis pi over 3. And the polar form for the complex number square root of 3 plus I is actually 2 cis of pi over 6. So pause the video and check this. Now, when I want to multiply these, let me just remind you what this notation means. When I write cis of an angle, what I mean is the expression that has cosine of the angle plus I times sine of the angle. So when I'm multiplying these two complex numbers, I'll be doing 2 cis pi over 3 multiplied by 2 cis pi over 6. I'm going to multiply the numbers 2 times 2, so I'm going to get 4 cis pi over 3 multiplied by cis pi over 6. Here is where it comes. The fantastic, wonderful property about cis that, let me write it here, if you have cis of alpha plus beta, this is the same as cis of alpha times cis of beta. So this is what we want to use. We're saying that if we want to multiply cis of two angles, we can find cis of the sum of the angles. And this is what I'm going to use over here. So I'm going to write that this is 4 cis of pi over 3 plus pi over 6. So this is 4 cis of pi over 3 plus pi over 6, that's just pi over 2. Yeah. Okay. So that was very quick to do because we are relying on this very important property. And this also gives us a geometrical interpretation of what is happening, because we can look at what's happening to the modulus when we multiply and what's happening to the argument. And what I'm saying over here is that when I multiply two complex numbers, the modulus of the multiplication, the new modulus, is the product of the ones I had before, and the argument is a sum. So I had over here two complex numbers that I'm going to draw very quickly. One of them was like this with the angle pi over 3, and the other like this with the angle pi over 6. And then I'm going to get a new complex number that actually lives here. That is the complex number 4 cis of pi over 2. But wait a minute, this should be the same as 4i, because we found the product in a different way, and that was what we got. But yeah, then we need to find that actually cosine of pi over 2 plus I sine pi over 2. What is this? Well, cosine of pi over 2 is 0 and sine of pi over 2 is 1. So this is actually for I, as we already knew. So here we checked that this works. So in general, if I want to write a formula, if I have complex numbers in polar form, let's say W given by R cis alpha and Z given by S cis beta, then to multiply them, my result will be a new complex number with modulus, the product of the modulus that I had before, and argument, the sum of the arguments I had before. So this is a much faster and a nicer in general way of multiplying complex numbers if we use the polar form.